In our last class, we discussed about a particular uh, point or particular problem. The problem states that whether the following statement is true or false, or we need to find some group, a group G, such that the group itself is non-cyclic, such that the group G is not cyclic, but every proper subgroup of G is cyclic. So, in fact, I took an exam in my last session. So, there I gave one question, but the question was not that interesting, but yet that has different meaning. The question says that give an example of a group, and that part was missing. So, that group, I just dropped this condition. So, such that G is the group, but every proper subgroup of G is cyclic. And if I drop this part, then suddenly there are plenty of such examples. But here, for example, if we consider any cyclic group, then that will be fine. Okay. But if I make some twist on it, for example, if I add such that the group G is infinite, so the group G is infinite, then not all cyclic group will do, but suddenly infinite cyclic group, for example, Z plus will certainly do. So my question initially, I started with a simple question, let G be a group such that every proper subgroup of G is cyclic. If I consider this group, let G be a group such that every proper subgroup of G is cyclic. If I need to find such group, then we know that any cyclic group will be sufficient. For example, any cyclic group, for example, Zn n greater than equal to 2 will be fine for that, right? Not only that, we could have also S3. See here, S3 itself is not cyclic, but every proper subgroup of it is cyclic. For example, if you consider any proper subgroup of it, who are the subgroups? For example, E is the subgroup. If I consider all subgroups of order 2, so this is one subgroup. If I consider E1, 3, then that is a subgroup. E2, 3 is a subgroup. Okay. Now, if I consider this E1, 2, 3 and 1, 3, 2, this is also a subgroup. So they are just all proper subgroups of S3. Mind that I mentioned about proper subgroup. Proper subgroup. Sometimes the question is asked how many subgroups are there. Note that S3 is a subgroup of itself. So if the question is asked all subgroups of S3, then along with this, you need to also include S3. But if the question is being asked that how many proper subgroups are there, then they are the only 1, 2, 3, 4, 5. They are the 5 proper subgroups of S3. And note that all of them are cyclic. For example, this is one pointing subgroup, so that's generated by E. This is generated by 1, 2. This is generated by 1, 3. This is generated by 2, 3. And this is generated by, it has 2 generators, this and this. Okay. So we can see that every proper subgroup of S3 is cyclic, but interesting fact is that S3 is not cyclic. So if I ask you the question, let G be a group such that every proper subgroup of G is cyclic, then any cyclic group will be sufficient. But if I make a twist on it and if I put a point like let G be a non-cyclic group, such that every proper subgroup of G is cyclic, then suddenly S3 is fine. But if I make little more twist, if I add, let G be an infinite non-cyclic group, infinite non-cyclic group, such that every proper subgroup of G is cyclic. So this infiniteness, addition of this term actually increased the problem, or the hardness of the problem increased a lot, manifold. So in my last class, I have already shown you the idea of the proof technique. So there we have considered a particular kind of subgroup. So we know that C star, that means all complex numbers, and if I just remove the zero, then with respect to dot, this is a commutative group, right? We have already seen few other facts that every subgroup of a cyclic group is also cyclic. Okay, and we consider a very particular kind of subgroup of C star. What is this subgroup? It consists of all such elements from C star such that z to the power 2 to the power n equal to 1, and this n actually varies. So 0, 1, 2, and so on. Okay, so first we already shown that this is a subgroup of C star. So no doubt that this is a subset of C star, but more importantly, this is a subgroup of C star. Subgroup of C star. So that we have already shown in my last video. Okay. So I claim that H is my group, and I can show that every proper subgroup of H is cyclic, but H is not cyclic. Okay. To prove that, first let us consider this groups. H of, say, I. H of I is all such Z belongs to C star such that Z to the power 2 to the power I equal to 1. Now I vary I from 0, 1, 2, and so on. Note that H1, Hi, so what is H0? H0 is Z belongs to C star such that Z to the power 2 to the power 0 is 1, that means 1. That means if I draw this geometrically, that gives me this point. So this is my H0 consisting of only one point, that means 1. So what is H1? H1 is also Z belongs to C star such that Z to the power 2 to the power 1 equal to 1. That means Z square equal to 1. That means Z equal to plus minus 1. So it consists of two elements. That means it consists of already this element in H0 and along with a new element. So this was my 1, this was my minus 1. Now what's H of 2? H of 2 is all such belongs to C star such that Z of 2 square equal to 1, and it consists of, you can understand that, 1 minus 1 I minus I. So you can see that already H2 consists of the elements of H1 as well as the elements of H0. So two more elements. So this is my I and this is my minus I. So now you can understand that H0 is a subset of H1, is a subset of H2, and so on. Okay. So each of this H1, H2, H3, they are cyclic, no doubt about that. They are cyclics. So this is also cyclic, this is also cyclic. So who is the generator of this? 1 is the generator. Who is the generator of this? Can anybody tell me who is the generator of 1 and minus 1? Who is the generator?
-1.
Very good. In case of H2, who is the generator? In case of H2, who is the
I.
I and
I?
minus I.
I
Both.
and
I
minus.
and minus I. Both of them are generated. Okay. So I and minus I, both of them are generators. Very good. So you can understand that each of Hi is a subgroup of H. No doubt about that. So each of Hi is a subgroup of H. Is it clear? Now I claim that you need to prove on your own. It's not very difficult. H equal to, can anybody tell me what is the relation of this H? How, what shall I write it here? Is a fill in the blanks. What should I write it here?
The
Union.
union.
Yeah. Yes, very good. So union of I equal to 0 to infinity H of I. Okay. So from the construction, you can understand that you can go on just increasing the points like this, like this, like this, but you cannot stop. You can never stop anywhere. You have to, because there exist infinitely many rational numbers on the circle. So you cannot stop. If you stop somewhere, then there will be rational numbers between, suppose you have stopped somewhere and that is the points on the circle, then you can understand that there exist infinitely many points in between. So you can also may also have another hi which will have these points, right? So you cannot stop anywhere. So intuitively you can understand that this is, so this part you need to prove. So this is your homework. Okay. Now, so what is my claim? Every proper subgroup of H is cyclic. That is our claim. So every proper subgroup of H is cyclic. That is our claim. Okay. So how to prove that? Is it clear, the proof in the claim? Okay. So let us have a look at this. So let take us any subgroup of this like this. So this is my H and take any subgroup, say K. What I need to show? I need to show that K is cyclic subgroup of H in this particular case. So H is already given. I am taking any proper subgroup of K. Let K be any proper subgroup of H. Claim. What is our claim? Anybody tell me? K, what K is cyclic. So that is our claim. Okay. Okay. Now I need to give a proof. Since K is a proper subgroup of H, there must exist some G here which is not within K. That's why this is proper. So as K is a proper subgroup of H, there exists some G belongs to H such that G does not belongs to K. That's why this is proper. That means some element of H is here which is not within K. That's why this is a proper subgroup of H, right? Mind that this G belongs to H. And what is the definition of H? That means for every element in G, there must exist some n such that G to the power 2 to the power n must be equal to 1. So what was the definition of H? H was all such Z belongs to C star such that Z to the power 2 to the power n equal to 1 and n varies 0, 1, 2 and so on. Since G belongs to H, so for that G, there must exist some n such that G to the power 2 to the power n must be equal to 1. Okay. As G belongs to H, there exists some n equal to 0, 1, 2, such that G to the power, so I may put say k, maybe say t. So n is already given here, so I just put some t such that G to the power 2 to the power t equal to 1. Any question till now? If you have any question till now, please let me know. Okay. So assume that no question. Okay. So what is this? So I claim that my K, the subgroup K, must be within H of 2 to the power t. Remember what is H of 2 to the power t? So claim K is a subgroup of H of 2 to the power t. Remember what was my H of 2 to the power t? Also Z belongs to C star such that Z of 2 to the power t equal to 1. Mind that H1, H2, H3, that's why I just defined. So it was not 2 to the power t, it was H of t. As per my notation, so I must erase this. So as per my notation, so it was H of t. Remember just H of t. So remember those things I just mentioned here. What was my H1, H2, H3? So H2, H3. So H2 means Z of 2 to the power 2. H3 means Z of 2 to the power 3. So H of t means Z of 2 to the power t. Okay. So according to our notation, it was my Z of H of t. So it was my claim. H is a subgroup of HT. Can anybody tell me why I am claiming this? Why I am claiming this? That H is a subgroup of H2, HT. Any claim? Why? Any proof idea that you can think of? Any idea? Okay, if not, so K is a subgroup. I claim that there must exist such that HT, so K must be contained within H of T. Okay, that is my claim. Okay, geometrically, if I write it, it should be within, G should come within this HT. So one thing you just try to remember, what was the idea of this HT? Sorry, what was the idea of this HT? It was like this, a circle. Some points are there within HT. Say these points are there within HT. Okay. And if HT, say this is, suppose these points are there within HT. So if I consider HT minus 1 or HT minus 2 and so on, all the points inside this will also lie within this HT. Is it clear to all of you? That's what we made it. H0 is a subset of H1, is a subset of H2 and so on. So all points having indices t minus 1, t minus 2, all the points inside this will must belongs to this. Okay. So what is our claim? Our claim is K is a subgroup of HT. If not, so if not, that means if K is not a subgroup of HT, then K must contain some Z, some point, some Z, such that Z to the power 2 to the power say S equal to 1, and this S should be strictly greater than K. First, try to understand this statement. Is it clear to all of you? Is this clear to all of you?
Say is greater than K or T.
Greater than T. Yes. Very good. Greater than T. Yeah. Is it clear to all of you? Then there must exist some T. Then, if not, oh, then this K. This K is fine. This K is the my subgroup. So this is capital K. Must contain some Z such that this. So if not means if K is not a subgroup of HT. Okay. So understand all subgroups of HT, all the subgroups of HT, say HT minus 1, they should look like this. And if K is not a subgroup of this, that means K must be bigger. That means if G to Z to the power 2 to the power T, so it must contain some element. If I make a power of this S, then that S should be greater than T. So let me come through an example. Then that will be clearer to all of you. Okay. Suppose this is my, say, HT is my, say, 1 minus 1, I minus I. Okay. And say K is a subgroup which is bigger than that. Okay. Note that K must be a subgroup of original K, original H. So by definition of H, so K must contain some element Z such that Z to the power n equal to 1. Now what I say, so here what is the value of HT? So T is equal to 2. Now what I say, this the value of n must be greater than 2. If not, then it should come within this. If the value of n is less than 2, in that case what will happen? Z to the power 2 to the power 1 equal to 1. That means the value of Z could be plus minus 1. So that's already within this. Then this K value, this K subgroup will be within H of T. But since this is not, that means it must contain some element G such that Z to the power 2 to the power n equal to 1 for some n that should be strictly greater than 2. So that is happening here. So here this is my n and this T was my 2. Is it clear to all of you? Any question? If you have, please let me know. Then I can again explain. Any question? If you have, are you comfortable with this argument? If not, then let me know. I shall again explain. Okay. So hope, is it clear to all of you? Okay. So I assume that it's clear to all of you. Then what is happening? So if not, then this will happen. Now note that again by similar argument, if S is strictly greater than T, if S is strictly greater than T, then what will happen? The G to the power, then g to the power 2 to the power t must be within k. Why k? Because if z2 to the power s equal to 1 and s is strictly greater than t, s is strictly greater than t, so this is my t value and this is my s value. So as just now I have mentioned, if this is something, the construction is like that, if s is more than t, then all the points within this t value, all the values of g that will come due to this t must be within this, all the values that comes through k. That means g to the power 2 to the power t belongs to k, or not g to the power t, g belongs to k. That means what we started with? We started with a point g which was not within k. But through this argument, we came here that g is within k, a contradiction. And why this contradiction came? Because we assume that this, if not, so if not, then what is our argument? K is a subgroup of h of t, h to the power t. So K is a subgroup of h to the power t. What is then your conclusion? What actually we are trying to show? We are trying to show that any proper subgroup of H is cyclic. And what you have shown, that you started with a proper subgroup K. It was our claim. So we started with K as a proper subgroup of H. Now we have shown that this K is a subgroup of HT. Now is the proof complete or any extra argument that we need? What is HT? Remember, HT is a cyclic group and K is a subgroup of a cyclic group. Then what would be your argument? Next argument is K is cyclic. And that's what we need to prove, that every proper subgroup of H is cyclic. So we started with K, any proper subgroup of H, and then we have proved that H must belongs to some of the K to the KT subgroup, and this is cyclic, so K is also cyclic. But we now need to prove that H is not cyclic. Okay, so K is cyclic. Is this part clear to all of you? K is cyclic. Is this part clear to all of you? Any question? Or shall I repeat once again? Okay. So I assume that you yeah.
So the contradiction part I couldn't understand. Can you please repeat it again?
Which one? Which part?
That contradiction part.
This contradiction part.
This one, that G belongs to K. A contradiction.
G belongs to K, a contradiction, where it is.
Okay.
Okay, this one.
Yes, sir.
This one. Okay. So as you see that, again, if you just try to remember what was our initial thing. So we started with, okay, let me again do something. So we started with a subgroup. So H was our original group and we started with a subgroup K. Okay, we took an element which is not within K. That's why this is a proper subgroup. That's why we can always find some G which is not within K. Okay, since G belongs to H, by the definition of H, there must exist, say, some T such that G to the power 2 to the power T equal to 1. Okay, I took T or something else. Let's see. I took yes. So g some t such that g to the power 2 to the power t equal to 1. So I took t, the same thing. Okay. So what I say, that there exists some t such that g to the power 2 to the power t equal to 1. Okay. Now you can consider the subgroup g of t that consists of all such z belongs to C star such that z of 2 to the power t equal to 1. First note that this g is belongs to ht. Is it clear? This g, then g is belongs to h of t. Why? Because g to the power 2 to the power t equal to 1, and that should be the case here. So g belongs to ht. So your ht is something here, h of t. Okay. So now I claim that. So it might happen that it contains gt. It may happen like this also, which contains g, but not fully contain k. But now our claim is k is a subgroup of h of t. That is our claim. Okay. So if not, then k must contain some element, say z, such that z to the power 2 to the power s equal to 1, and that s must be greater than t. Why so? If s is less than equal to t. So why so? Reason is, if s is less than equal to t. Now what happened? By the definition of this construction, all the z to the power 2 to the power s, so all such z that satisfies this z to the power 2 to the power s must be within this h of t. In that case, z will be within h of t. But we claim that if not. So that's why this s must be strictly greater than t. Clear? Now what will happen? Now consider the g of then 2 to the power s. So look at this. Since s has some element z such that z to the power 2 to the power s is greater than t, and s is greater than t. So when we consider all the elements which satisfies this, if you draw like this, so all such points which satisfied by this, say this 8 points. Okay. Say s value is say 3 and t value is say 2. So all the points that are satisfied by this, so they are the 8 points, and t value is 2. So suppose my t values are like this, so they are all these t 4 values. Okay. Now what is happening then with g to the power t? So t is 2, t is now my 2. That means g of 2 square equal to 1. Then what are this g? Then g must be this red portions, and that is already included within the elements for z 2 to the power 3, because they are all the 8 elements, and the red portions are the for t equal to 2. That means g to the power 2 to the power s equal to 1 implies, sorry, g to the power to the power t, it was t. T equal to 1 implies G belongs to where? G belongs to K, because K is Z is within K, and Z satisfies this property. That means K contains all the 8 points. So all the 8 points means all these 4 points. As a result, G must be within your K. But what was your claim initial starting up? So it was K was a proper subgroup. K was a so K was your, I mean K, not K, but G was within K. But G was initially started with, we took G which was outside K. That's it was a proper subgroup. But now you see that if it could be the case, then G belongs to K, and that is a contradiction. And that cannot happen, right? So that's why you can say that we get a contradiction, and so the contradiction happens because you have taken that K is not contained in HT. So K must be within HT, and HT is a cyclic group. So K must be a cyclic group. Is it clear to all of now? Is it clear now?
Yes, sir.
All of you? If you tell me, I will repeat thousand many times, no problem. But you let me know that where is your problem. Then I can repeat as many times as you want. Is it clear? Okay. So now one thing we need to show that H is itself not cyclic. So H is not cyclic. Any guess why this is so? From geometry, you can very easily say. So we have already shown you that I have given you that homework that H of I equal to 1, 0 to infinity. Okay. So if this is a cyclic group, so if possible, let H be cyclic. Let H is generated by H. Okay. Since this condition is satisfied, that implies H belongs to capital H of some, say, T, for some T. Okay. Then, so this is cyclic group, right? And H is a generator of the whole group. Now, if you do, like if you do, so now can anybody tell me that what could be the reason that it cannot be a cyclic group? Any guess?
স্যার বিগার এইচটি থেকে এইচটি প্লাস ওয়ান এগুলোকে তো জেনারেট করতে পারবে না।
Exactly. So now, if this could be the generator, and if this is within this, then how can it generate the bigger groups, which is, say, S, which is greater than T? Then this H cannot be able to generate the subgroup H T plus 1, H T plus 2, and so on. So suppose some generator is there, and so geometrically you can think like this. Say there's 4 generators are there, Okay, and if this is, say, I is the generator here, and will I be able to generate this point? Other way around, this point can generate this, but will I be able to generate this point? That's why. So that's the idea. Is it clear to all of you? Is it clear?
Yes, sir.
Okay. So now we have finished that part, but it has really lots of interesting results are there within this small example. So that's why this is very important. So another group is also a very good important, that is again a similar type. So all such Z belongs to C star such that Z to the power n equal to 1. If I stop it here, then certainly this is the nth root of unity, but instead of stopping here, I'll just continue like 0, 1, 2, and so on. Just like my previous case, but previous case it was 2 to the power n, but now it's only this. Okay, so the first idea is to prove G is a group, and suddenly a subgroup of C star. Okay, so that is also very interesting. We'll come to it later on and show you, and you can see that every, so if I ask you the question, is every proper subgroup of G is cyclic? What is your idea?
Yes,
If I
sir.
ask you this question, is every proper subgroup of G is cyclic?
Yes, sir.
How will you prove? Anybody? So it's true or false? Somebody says it's true. Any other? Just try to think. Just now what I explained, the example.
Sir, G will be the union of when n equals to 0 and n equals to 1 and n equals to 2 or everything.
Yes.
আর স্যার যেটা হবে এইগুলো প্রত্যেকটার ইউনিয়ন, এবার ইউনিয়ন হওয়ার জন্য সেটা স্যার এন রুট অফ ইউনিটটাকে, ইউনিটটা হবে এটা সাবগ্রুপ, তার জন্য সেটা সাইক্লিক হবে।
So you say that every proper subgroup of G is cyclic. Okay. Just now we have shown you that H, that is just now that we described. G belongs to C star, so that J 2 to the power n equal to 1, n equal to 0, 1, 2, and so on. What is the relation between this and this G? What is this relation? This is my H and this is my G. What is the relation between these two groups?
So
H is a
H is a
এটা
subgroup
subset.
of
সাবগ্রুপ অফ জি।
H is a subgroup of G.
Subgroup of this. So is this cyclic? Is this group cyclic, H?
No, sir.
Just now we have seen that this is not cyclic. That's what we proved. And this is a proper subgroup of G. So that's why not every proper subgroup of G is cyclic in this case. But we have chosen this in a smart way. That's why I have chosen, instead of n, it was 2 to the power n. In that case, that property was satisfied, that every proper subgroup of H is cyclic. But its same thing is not happening. Every proper subgroup of G is cyclic. Is it clear now? So the answer will be this false, because the counter example is this H. So H is a proper subgroup of this group, but H is itself not cyclic. but every subgroup of H is cyclic. Clear? So it's quite interesting group. Is it clear to all of you?
হ্যাঁ স্যার।
Okay. So now I will go to some subgroups, some special type of subgroups. So one subgroup for a special group, Sn, you remember, right? You all remember Sn, the symmetric groups, symmetric group on n elements. So S3 was our symmetric group. Okay. Now, so in S3, we had the elements are of this type. So E, 1, 2, 1, 3, 2, 3, then 1, 2, 3, 1, 3, 2. So they are just the 6 elements of S3. Now in Sn, there is a term called transposition. Transposition. What does it mean? A cycle of length 2 is called transposition. A cycle of length 2, that is called transposition. Okay. Now you can see that, so they are just one cycle of length, so they are transpositions, but this can be written as 1 3 composition 1 2. Now if I make 1 3 composition 1 2, quickly can you tell me what would be the case? So 1 goes to 2 and here 2 goes to 2, so 1 goes to 2, 2 goes to 1 and 1 goes to 3, so 2 goes to 3 and 3 goes to 3 and here 3 goes to 1, so 3 goes to 1, this is complete. So similarly I can write it 1 2 composition 1 3. Okay, that means every cycle can be written as a product of transpositions. Is it clear to all of you? So every cycle can be written as a product of transposition. Now quickly, can anybody tell me how this E can be written as product of transposition? Quickly, how E can be written as product of transposition? You know.
So 1 1 into 2 2.
1 1. What does it mean?
1 2 into 1.
Very good. So 1 1 is not a cycle of length 2. So 1 1 means 1 goes to 1. So you do not write anything for that. Okay. So transposition must be of length 2. So somebody says correctly 1 composition 2 into 1 composition 2. It can also be written as 1 composition 3 into 1 composition 3. It also be written as 2 composition 3 into 2 composition 3. So this writing may not be unique, but so it can be written as product of transposition. Now, why this term is important? Because two important terms comes from here. So one is even permutation, another one is odd permutation. And this depends on the number of transpositions. If the number of, if some permutation is a product of even number of transpositions, then we call it even permutation. While if some permutation is written as the product of odd number of permutations, then we call odd permutation. So can anybody tell me What should be like E? E is even permutation or odd permutation? Even, because E can be written as product of even number of transpositions. Product of even number of transpositions. Two transposition product. So E is an even permutation. What's about 1, 2?
Odd.
Odd. Similarly 1, 3. Similarly 2, 3. What's about 1, 2, 3?
Even.
Similarly 1, 3, 2. Now the collection of all even permutations, if I consider, it can be shown that that is a subgroup of Sn. So for example, this is a subgroup of S3. So this is nothing but collection of all even permutations. And that is denoted by An, and that is known as alternating group. Group on n elements. Okay, so here we call it, this is A3, and it can be shown that this A3 is a subgroup of S3, and that is known as alternating group A3. Okay, but the collection of all odd permutations is not a subgroup. Why not? Yes, not a subgroup even. Okay, but the collection of all, so you cannot miss anything, collection of all even permutations, that will be a subset of S3 or Sn, and that is denoted by An, that is known as alternating subgroup. So this is one example of a very particular kind of example of a subgroup. Now I will consider another class of subgroups. So let G be a group. We consider a set ZG, all such element of G such that GA equal to AG for all A belongs to G. Can anybody tell me what is I am writing here? All such elements of G such that GA equal to AG for all A belongs to G. What it says actually, intuitively, what it says?
Collection of those elements which commutes the all element of G.
Very good. So it is all such elements. So all such elements of G which commutes, which commute with all the all the elements of G. Okay, so that's the idea. So this is why it's for all. Now suppose if I consider Z of Z, can anybody tell me what would be the Z of Z?
Z.
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 Because it's a commutative group, so every element commutes with other, that's why the whole group. So this is called the center of a group, center of a group. And it can also be shown that, so that can be considered a theorem. Let G be a group, then the center of G denoted by ZG is a commutative subgroup of G. So not only it's a subgroup, but ZG is a commutative subgroup of G. For example, let us try to find what could be the center of S3. So S3 we know. So now the question is, what is S3? That means we need to find all such G belongs to S3 such that G composition A equal to A composition G for all A belongs to S3. Okay. Okay. So first let us have a look, and then we'll show that this is really a subgroup of G, and that will certainly be commutative subgroup of G. So let us have a look at this. Can anybody tell me what is Z of S3?
Identity.
The identity.
Yes. And no other element will commute with each other. So take, for example, take some element. So there is no doubt that E commutes with every element. So E will certainly be there. But we need to prove that no other element. For example, take 1, 2. Okay. So we need to show that 1, 2, and suppose I consider 1, 2, 3. And what is 1, 2, 3, 1, 2? Quickly tell me what is 1, 2 composition 1, 2, 3. So this is 1 goes to 2 and 2 goes to 1. So 1 goes to 1, I don't need to write this. Then 2 goes to 3 and 3 goes to 3. So 2 goes to 3. 3 goes to 1 and 1 goes to 2. So cycle is complete. Let's see what is happening. So here nothing is there. So here 1 goes to 2 and 2 goes to 3. So 1 goes to 3. Here 3 goes to 3 and 3 goes to 1. So 3 goes to 1. 2 goes to 1 and 1 goes to 2. So 2 goes to 2. So you can see that 1, 2 composition 1, 2, 3 is not same as 1, 2, 3 composition 1, 2. So what does it imply? Neither 1, 2 nor 1, 2, 3 is within center of G, because it is not communicating with this and this is not communicating with this. So none of them are within center of this. Similarly, you can prove that with other elements. So you can check with other elements, for example, say 1, 3 and then 1, 3, 2, maybe you can check. Then you will able to see that this is not also within the center. Both of them are not within the center, and so on. So you will able to see that E is the only element of S3 which is within the center. Okay, now we will come to the proof of this, that okay, center is really a subgroup of G. So remember, what is the definition of center? The definition of center is all such elements which communicates with all the elements of G. Okay, so now I'm going to show you that center of G, ZG, is a subgroup of G. That we need to prove. Okay. So how to start with? Anybody tell me how to start with formally?
যেহেতু EG compose G equals to G compose EG for all G belongs to capital G, so EG belongs to ZG, so ZG is non-empty.
Could you repeat once again?
যেহেতু EG compose small g equals to
Yes.
G compose EG
Very good.
for
So
all
EG
G
equal to GE
G for
equal
all
to,
G belongs to capital G.
for all G belongs to G, E must
So
be within
ZG.
ZG. So
So
this
ZG
part
is
is
not
very important. That's why you say that at least one element is within ZG. That's why ZG is not equal to empty. So many of the students I have seen from my experience that they just skip this step. But this step is very important. Unless you have at least some elements within ZG, there is no point of showing that ZG is a subgroup, because the definition of a group or a subgroup, it starts with a non-empty set. So you need to prove that this group is a non-empty group. So that's why it's very important. Okay, so the first thing is that ZG is non-empty. Now you have some, you can take some two elements. So let AB belongs to ZG. Since it is non-empty, you can have the liberty to take two elements, any two elements from ZG. Okay. So what is your claim? To show, what you need to show? To show A B inverse belongs to ZG. And if you are able to show that, then you are done basically to show that this is a subgroup of G. Okay. So as A B belongs to ZG, so A dot G equal to G dot A and B dot G equal to G dot B for all G belongs to G. Now from here you can write it like, so if I multiply both sides with B inverse, okay, so B inverse then BG equal to B inverse of GB. Now you can apply associative property, so that becomes E. So that means G equal to B inverse GB. Now if I multiply both sides with B inverse from the right, so G B inverse, that becomes B inverse GB and then B inverse. Now if I combine these two through associative property, then it becomes B inverse G. So what I have seen that G B inverse equal to B inverse G, and that is true for all G belongs to G. So what is your conclusion then? What is your conclusion? That implies,
B inverse belongs to ZG.
so B inverse G, very good, belongs to center of the group. Clear? So I started with B and I have shown that B inverse is also in center of G. Now what I need to show that this belongs to G. That means I need to show A B inverse into G should be equal to G of A B inverse. If I able to show, then we are done. Now this is equal to A B inverse of G because associativity, and just now we have shown that B inverse is also in center. That means it can communicate, or it I can so it has the commutative property. That means you can have this, and then again A belongs to G ZG, so it can also you can have the commutative property with A, so B inverse. And so you start with A B inverse G, you end up with G A B inverse. What does it mean? And that is true for all G belongs to G. That implies A B inverse belongs to Z of G. That implies ZG is a subgroup of G. Now I need to show that this group is a commutative group. ZG is a commutative subgroup of G. So take any two elements from ZG. Let AB belongs to ZG. So A and B communicates with each element of G. Then A into B. So it will also communicate with each other. So BA for all AB belongs to ZG. What does it mean? That implies ZG is a commutative subgroup, commutative subgroup of G. So we are done. So just now what we have seen that Z of S3 equal to E, and you see that it has only one element, hence it's commutative. Again, just now we have seen that Z of Z is again Z, and this is a commutative. So center of a group is always a commutative group. Clear? Now we are going to show little more detailed about what is center of arbitrary Sn. If I ask you, okay, at the end I will ask you this question. Suppose now what I'm going to prove is that center of Sn, where n is something I will tell you later on, and I will write it later on, something is E. Okay, center of Sn is E. That I'm going to prove. Which I left something that I'm going to write something somewhere. Okay, I'll just give you the basic idea. So start with say 1 2, say 1 2, or say start with AB and start with A B sorry BAC. Okay, maybe other things, other things are also here, but it start with AB and then BAC. Now what is about AB composition BAC, and what is BAC composition AB? Tell me, what can I say about? So B goes to A, and this is, so B goes to A and A goes to, so B goes to A and A goes to B. So B will be there. Now A goes to C and C goes to C. So this is AC, and C goes to B and B goes to A. So C goes to A. And what's about here? Here is A goes to B and A goes to B and B goes to A. So you don't need to write A. So B goes to A and A goes to C. So B goes to C. And then C goes to C and C goes to B. So this is closed. Okay. So I say that this idea will help you to show that Sn equal to E. How? What is the idea behind that? So it's my question. And what should be this case? Now, if I ask you, suppose I have proved this, okay? Suppose I have proved that this is equal to E, and if I ask you the center of Sn equal to E, n greater than equal to 1, true or false? True or false? If I
False.
ask you,
False.
why?
N equal to 2. If n
Very,
equal to
very good. Then that is
S2.
S2, and that is commutative. Similarly, for S1, that is E, and that is also commutative, that is S1. So it's not E, right? So this is fault. Many of the students, they miss this kind of small statements during the exam. So here it should be n greater than equal to 3. That's why I just I put it blank, because I just wanted to point it out. Some of the students, they miss this. They think that z of Sn is E for all n. It's not true. For this 2 value, this is not true. That's why this is true only for n greater than equal to 3 or n equal to 1. For n equal to 2, this statement is false. Okay, but I have given you sufficient hints to think about the problem, that why the center of Sn is E. Now think yourself and try to develop a logic. So as you can understand that n is greater than equal to 3, so you must have at least 3 different alphabets. For example, here it was like 1, 2, 3 or more. It could be 3 or more. So here I can think of they as an alphabet. So that's why I had taken A, B, C. So that is guaranteed by the fact that the value of n is greater than equal to 3. Otherwise, if the value of n is 2, then you cannot have 3 different alphabets. Alphabets means this 1, 2, 3, some of these 1, 2, 3 values. So at least you will have three of them, 1, 2, and 3, and that's the hints. And now you need to read a bit about Sn. I have given almost all the ideas of Sn, but still you need to look at Sn and then how An can be represented as three cycles and all, three cycles, product of three cycles. An could be written as product of three cycles. As you understand that any element of Sn can be written as a product of transpositions. But for An, it has some special property. It can be written as a product of three cycles and all. So few more properties are still there in Sn that you have to explore. And while exploring this, you will certainly be able to get this idea what is the center of Sn for n greater than equal to 3, and that may help you a lot while thinking or developing your ideas. Okay, so I will stop it here, and in the next class I may start with the cosets and all, cosets, and maybe if I time permits I will go to normal subgroup. Any question if you have till now? Any question? So if not, I will stop it here.